Hello, everybody. Welcome back to Chemistry with Mr. Adelson, the version for Chapter 12. So today in Chapter 12, what we're going to be talking about is bonding. Now, if you want to be able to remember the difference between a covalent and ionic bond, covalent bond yells at an ionic bond. Didn't anybody ever teach you to share? The joke there being that covalent bonds share and ionic bonds transfer electrons. Ha, 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 ha. Very funny, I know. So chapter 12 is all about bonding. There are different types, different charges, Lewis structures, and a really fancy valence shell electron pair repulsion. Okay. Our learning objectives today, I will be able to identify and describe different types of chemical bonds. I will be able to construct a Lewis and electron dot structure. Okay. There are simplified objectives if you want to go in and figure out how to do those things. And these are funny memes. This isn't a particularly important slide because we're not in school, but it's from a movie called Office Space. I've actually never watched it in whole. You guys probably haven't either. Okay, so ionic structure. I think we already talked about this a little bit, but I'm going to go over it again. It was in the last unit. Cations are going to be smaller than their parent atoms. Okay. It's because they're going to return to a smaller noble gas electron configuration. So, as we learned earlier with electron configurations, like with Li, what Li did is when it becomes stable, it goes to the nearest noble gas. It's atomic number 3, so the nearest noble gas to it in atomic number is atomic number 2. So atomic number 2 is helium, which is on principal energy level 1. It returns to a smaller principal energy level, which makes it smaller. That's because it's a positive charge. Okay. Anions, however, will get bigger because as you get closer to the right side of the periodic table, your atoms are getting smaller and smaller and smaller. And then once I get to that noble gas electron configuration, I kind of ease up my shoulders, I relax a little bit because I'm getting stable. Okay. More electrons expand the cloud. The anion is happier. So a different way to think about that is when I add that one electron, all of the electrons repel each other a little bit more. That's a different way to think about it. Not technically right, but it's a way to help you remember it. Okay, and you can see examples up in the top right corner of certain types of atoms and how they expand when they become an ion. So F becomes F minus, and if you're wondering what that unit is, it's angstroms. And what an angstrom is, I believe it's 1 × 10⁻⁸ meters. That's a very small unit of measurement. Okay. Chemical bonds. By definition, a chemical bond is a bond that holds 2 or more atoms together. Now, don't think that a single chemical bond can be connected to more than 2 atoms. It can't, but like a chain of bonds can. Okay. Any bond can be broken. And a bond is created by the exchange of electrons. Sometimes you'll have double or even triple bonds. Okay, double bonds are stronger and shorter, and triple bonds are even stronger and shorter than that. And the strength of a bond, which we will talk about, is measured by the energy that is required to break that bond. Now, if you're talking about ionic bonding, it's the strongest because the molecules are completely happy together. What the other one needs, we find in the other element, just like a good relationship. Whatever you need, you can find in the other person. That's what makes a good relationship. Some of you out there probably know that. One moment, I'm recording. Oh, feel free. Okay. See ya. So, sorry about that. Anyways, the happier they are, the more energy it takes to break the bond. So, just going in order, the bond strength goes ionic bonding. Then there's a special type of bonding that we talk about called hydrogen bonding. Now, when we talk about hydrogen bonding, I'll skip ahead a little bit. Hydrogen bonding is especially strong because hydrogen, as we all know, is kind of a weird element. It's kind of a metal, kind of a non-metal, but if we had to say, it's a non-metal. But its electronegativity is so low that when it bonds to some things, that it kind of behaves really close to an ionic bond, even though it's technically a covalent bond. So if I'm talking about like HF, that's hydrofluoric acid. When those two things bond, it's a very strong polar covalent bond and very, very close to being an ionic bond. Okay. So it's especially strong, and it's called hydrogen bonding. Now, don't mistake hydrogen bonding for being anything that hydrogen is bonded to. Because, for example, if I have H bonded to H, that's not hydrogen bonding. If I have H bonded to C, that's not hydrogen bonding, because those are non-polar. Okay. Hydrogen bonding is H bonded to pretty much anything else than the two things I just told you. Okay. So types of bonds. A single bond is called a sigma bond. Now, this kind of sounds like a weirdly phrased. It's the strongest single bond. Okay. Because when you're talking about a sigma bond, it's strong. It's stronger proportionally than a pi bond. Because what a pi bond is, it's in that double and triple bond. Okay. Because a double bond has a sigma and a pi. That sigma bond is the strongest one. Okay. Now, you don't need to know what a sigma bond and a pi bond are. You just need to know that they're relative strengths to each other. A triple bond contains one sigma bond and two pi bonds. Okay. And it's the strongest commonly occurring bond. There are some, I'm sure, out there somewhere that are crazy, but in the highest number of bonds that you'll ever see is 3 in this class. Okay. Ionic compounds, a result of when opposite ions form a compound. So most people say it's a metal or non-metal, but I do not like that definition, because if I think about NH4 plus and Cl minus, this is not a metal. This is a positive ion, and this is a negative ion, and they would form ammonium chloride. Okay. And an important point is you can have non-ionic bonds within an ionic compound, because think about NH4. That's technically a covalent bond because you're N bonded to H's. Okay. But when I bond with Cl, I end up forming an ionic compound overall. Okay. Because it's a positive ion and a negative ion. And as we already talked about this, transferred share and unequal sharing. It's special type called hydrogen. We already talked about that too, so I'm going to skip over that. Covalent bonding, as I said, is between nonmetals. Sometimes I call them gases, and that's just a mistake that's been ingrained in me by other chemistry teachers throughout my life. They do not call them gases. That's incorrect. You have to call them nonmetals. And remember, those are nonmetals are things to the right of the metalloids. Okay. And then everything else here, you can pause the video and just kind of read for yourself. We've already covered that, so I'm not going to spend too much time over it. Name the bond type. So you can go through, pause the video. I'll give you like a second or two to pause the video. Okay, so the first bond is going to be hydrogen bonding, specifically polar covalent. It's hydrogen bonding. It's a type of polar covalent that's especially strong. NaCl is ionic because Na is a metal, Cl is a nonmetal. C and H is nonpolar covalent. This is also nonpolar covalent because it's shared equally, and this is polar covalent. Okay. Polarity. Now, as you'll see here, there's a table of electronegativities. You do not need to memorize this. You do not need to know this. If you ever need to reference this stuff, it will be on your test as a diagram. Okay. Now, I may have said 0.5 earlier, and 0.5 is technically right, but in your book it does say 0. But I know for a fact that C bonded to H is a nonpolar bond. And H, as you can see, is 2.1 there, and C is 2.5. So that kind of tells you. So personally, I'm just going to go ahead and change this. I'll leave it there because I just don't want people to mess up what their book says. Okay. If it's different than electronegativity, hold on a second. So if your difference in electronegativity is greater than 2, it's ionic. If it's between 0.5 and 2.0, it's polar. If it's lower than 0.5, it's nonpolar. Okay. By the way, HF has what's called a dipole moment. If you're dealing with a polar molecule, and actually technically you have dipole moments in ionic compounds, but it's less important based on the chemistry inside because it's not being shared. Okay, so a dipole moment, it means exactly what the word says. Dipole, it means it's got 2 poles. So one of them is positive, one of them is negative. Okay, so the positive end of the molecule will be the cation, or whichever one is less electronegative. And the negative end is going to be the more electronegative. And as you can see in the bottom right corner, this kind of tells you how to draw a dipole if you needed to. Okay, you will never be asked to draw a dipole, but do know it looks like a little musical note there. And then there's a little plus sign. It's called a partial charge. The reason it's called a partial charge is because it's only like that for a split second because those electrons are being shared back and forth. Okay. And then on the other side, it's negative. So we do the partial charge negative. And then we've got a little arrow showing where the electrons are going. Now, there are some cases that are unique. Okay. Now, the reason I say that is because you can have bonds that are technically polar bonds, and the molecule itself will end up being nonpolar. Now, the reason for that is symmetry. Okay. When we're talking about polarity, what we're talking about is there a charged end? Okay. And if I got a symmetrical molecule, what's going to happen is the way those electrons are shared is that you're going to end up with not any charged ends. So you can have a weird molecule like, for example, CF4. But if I draw out CF4, what it's going to do is it's actually going to pull the electrons in equal directions against each other. So imagine you got a tug of war and everybody's pulling the exact same amount from each other. Does the rope move? And the answer is no. Okay. It's the same concept, right? If I'm pulling the same amount, like if I've got C in the middle of that tug of war and I've got F pulling on both sides, trying to move C out of the middle and it doesn't move, then it's going to be nonpolar as a molecule. Okay. So that's something to consider, and that will be important later on because we start talking about bond geometry in this chapter. Okay.
Teachers, please pardon the interruption.
One moment.
I need you to check an email that just came from Ms. Deason regarding attendance and attendance procedures. Please read the email, and if you have any questions, please make sure that you call the front office. You can call Ms. Deason, or you can call me or Ms. Harris or probably Mr. Barnes as well. It's very important that our students are checking in for each period. However, we do not want them receiving 8 different phone calls from us today, so just read your email carefully and please let us know if there's any questions, and we will come and answer those just as quickly as possible. Thank you.
But as I was saying, this is a lot easier when you only have 2 atoms, because 2 atoms, a polar bond is a polar bond. That's it. Okay. Then we go over to stable electron configurations. All molecules want a full valence shell. This is called the octet rule. Generally speaking, there's also something called the duet rule, but generally speaking, octet rule is the way to go. Okay. And then we start talking about Lewis structures, which is actually the main goal of this chapter. First, you take an element and you surround it with dots. Okay. Like fluorine. Now, what these dots represent are the number of valence electrons. Okay. So how do I know how many valence electrons that I have? Look at a principal energy level. Okay. Just like with the electron configurations, count how many electrons are in that outermost ring. Now remember, if you're talking about the transition metals, those do not count as valence electrons. So for example, if I'm talking about Br, which is bromine, That's atomic number 35. That would be 7 valence electrons. Because I'm gonna go through, I'm gonna count all the valence electrons that it gets it from. Okay. You have K, you have Ca, you have Ga, you have Ge, you have As, you have Se, and then you have Br. So that's 7 valence electrons. Okay. So you're going to see why this is important just a little bit later. Now you look to the right here and you can see examples. So group 1 is going to be 1 dot, group 2, 2 dots, group 13, 3 dots, 14, 4 dots, 15, 5 dots, 16, 6 dots, 17, 7 dots, and 18 has 8 dots except in the case of He. Okay. Now, I want to draw your attention to this bullet right here, because a lot of people make a mistake here once we start Lewis structures, and you'll understand where I'm coming from later on with this. Just because you see 1 dot here, when I bond with, let's just say I bond with Cl, and I form a bond, which means a bond is composed of 2 electrons, one from one atom, one from the other atom. That doesn't mean I've only got 2 electrons on Na. What Na does is it takes that electron that it has and gives it to Cl. And then what Na will do is it will drop down to the electron configuration of Ne. So it actually has 8 electrons on it, okay? So talking about Lewis structures. Bonding involves only the valence electrons. It does not bond any of the core electrons, okay? At least a pair of electrons must be used for a bond. You can never have a 1 electron bond, okay? Lewis structures are also referred to as electron dot structures. Each of the atoms in the bond must have a full valence shell to be stable. Now, once we get into more complicated Lewis structures, the only thing that can possibly not have a full valence shell and still maybe form is the central atom, but it will be unstable. Okay, when I say central atom, that means a lot of atoms are bonded to that one atom. Okay, and we'll talk about that here in a little bit. And what we're going to do is we're going to manipulate the available dots any way you can to get full valence shells for all of the atoms. Okay, all of the elements on the periodic table want full valence shells. Just remember that there's a difference between shared and transferred electrons. Okay. This is also important. Electrons that are left over or not in bonding must be in a pair. You can't have an electron out there just floating by itself. Okay. It will be denoted by 2 dots to the side of a molecule. Generally speaking, we only show lone pairs on the central atom. Why is that? Because when we're talking about our bond geometry, in other words, how the bond kind of orients itself to other bonds, it's only important with the central atom. Okay. And they do not participate in bonding, but they have a stronger repulsion than ordinary bonding electrons. And sometimes an atom will have more or less than an octet, and it can only be the central atom. I just talked about that. And by the way, if the outside atoms were unstable, they would simply just not bond. That's why outside atoms cannot be unstable. Okay. Sometimes elements may not be able to have a stable molecule. We will almost always have a way to get a stable configuration. I think I may give you one that gives you a stable or gives you an unstable configuration throughout the year. Okay. If they are unstable, it means that they don't have a full valence shell, or it is too full. Okay. I do want to point out though that this is just an example because it's ionic. It doesn't really have 6 electrons on it, but because it gives away the 3 valence electrons it does have, it's going to be an ionic bond with F. So it's actually really stable. But I just want you guys to use this as an example of something that might pop up. Okay. If this was the case, B would be bonded to F, and all 3 of them would be single bonds. Okay. Now, I might be speaking Greek to you right now, but trust me, I just need to get through all this, and then we're going to talk about it. But for what would happen is it would appear like B only had 6 electrons on it. And if that was the case, what would happen is there you go. What would happen is B would be unstable. Okay. Okay, this is a good stopping point so we can flip over. And we can start talking about Lewis structures and actually doing some examples. So when we're talking about Lewis structures, I'm trying to get everything to be satisfied. Where this really comes into play, though, is covalent compounds. If I'm talking about ionic compounds, this isn't really that big of a deal because ionic compounds are just going to pair up with an anion and they're going to give all the electrons away. Okay, so metals are cations, nonmetals are anions. They'll just get together. It'll be very simple. But if I'm talking about covalent compounds, it's actually really, really difficult. Okay, so first off, let's start out with CH4. Okay, starting out, you can put these dots anywhere, but I generally know where stuff's going to go just when I hear it because I've practiced this so much. So do know that you can put dots however way you want. You can do it like this. You can do it like any way you want, okay? But I'm going to do it a slightly different way. Do it whatever way you want. So what I'm going to do is I'm going to look at C. C is in group 14. That tells me that I have 4 valence electrons, okay? Forgive my poor penmanship, okay? So C wants to have an octet. It is in a chemical CH4, okay? This is a pretty simple one, okay? That means I'm going to have H is bonded to C's, okay? Do know that H's will never be involved in a double bond. They will never be bonded to more than one atom, okay? They are only involved in one single bond all the time, okay? Now, H is in group 1, which means it has 1 valence electron. So, C needs 4 more electrons to form an octet. And it just so happens that H has 4 electrons to give it because there are 4 of them, okay? Now notice, when I form these bonds, I have 2 electrons that form for all these bonds. Now, I'm going to do this for speed's sake, but do know that you don't have to do this. That's a bond, that's a bond, that's a bond, that's a bond. Now, what I'll notice is that throughout the year, if I just do this, people will start writing their bonds like this, like a dotted line or something. You don't have to do that, okay? You can just write a line, okay? So that would be an example of a stable molecule. Now, how do you know it's stable, okay? H has a duet. It's one of the few things that likes to have a duet, okay? All H's have duets. And remember, they're shared electrons. So H has access to these 2 electrons. This one H has access to these 2. This H has access to these 2. And that H has access to these 2. Remember, it's sharing. They're going back and forth really, really quick, okay? And then I want to figure out how many electrons are on C. Well, 2 in this bond. This will be 4. This will be 6. And then that will be 8, okay? Now let's do one that's a little bit more challenging, okay? Let's try the chemical NF3. I want to see the Lewis structure of NF3. Can you tell me? This one's a little bit more challenging, okay? You can try on your own if you want. Just challenge yourself. I'm going to give you the answer pretty quick, okay? So first off, N is in group 15, which means it has 5 dots, okay? You might not be able to see those. I'm going to get a little darker, okay? 5 dots, okay? There are 3 F atoms. In F, just like in group 1, it only has the ability to bond once. And if it doesn't do that, it's not going to like whatever situation it's in, okay? Which would probably mean it's going to leave, okay, that situation. So F, each F has 7 dots. Why do I know they have 7 dots? Well, they're in group 17. That means that they have 7 valence electrons. And I have 3 Fs. So each of these Fs needs 1 bond. That means each of them needs 1 electron from N. So this is a bond. That's a bond, and that's a bond. So now we know that they're all bonded. Let's ensure that they have 8 electrons, okay? So 8 electrons. 1, 2, 3, 4. Let me get a little bit closer. 5, 6, 7, 8. And these two are shared between both of them, okay? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay. Now let's look on N. 1, 2, 3, 4, 5, 6. Huh? I don't see 8 bonded there. But there is something else to notice. I have a lone pair of electrons on N. Okay. So that means that I have 8 electrons on N. Okay. So this is a stable molecule. Now let's try a little bit more complicated one. Okay. Let's try CO2. Most of you would probably think, well, CO2 is pretty easy because I know CO2 is carbon dioxide. Well, let's test that. First off, C. From earlier, we know it's got 4 valence electrons. O is in group 16, so it's got 6 valence electrons. Remember, I put dots the way I put them. You can put them however way you want to until you get to the end. In that case, they should be in the right spot. Okay. But once you start, you may not be sure. So now that you look at this, O has 6 electrons. For it to obtain 8, it needs 2 bonds from C. Okay? Now you may ask yourself, how do I know that C is a central atom in this case? How do I know it's not an O? Well, that's because, generally speaking, the cation ion is going to act as a central atom, generally speaking. Okay? Like I said, generally speaking. Okay? Or specifically, one moment. Hello, this is Mr. Ellison's room. I'm on recording right now. 106. Thanks. Thank you. Okay, so going through this, the C's need 4 bonds. And the only way that you can accomplish 4 bonds and have everything have an octet is for C to be in the middle. Okay. So first off, I need to realize that C is going to have all of its electrons participate in bonding. Okay, because each O needs 2. And C needs 4. So that means O is going to give 1 to C and C is going to give 1 to O. And then same way there. That's a bond, that's a bond. Okay? So what you're going to see is that's 2 double bonds. So let's count right here. How many electrons does O have? 1, 2, 3, 4, 5, 6, 7, 8. So 8 on that O. 1, 2, 3, 4, 5, 6, 7, 8. Well, that's 8 on that O. 1, 2, 3, 4, 5, 6, 7, 8. So everything's got 8 on it. It's a very stable molecule. Now here's a little trick question for you. Question. First off, is this polar? Is a C and an O bond polar? Your answer should be yes. Okay? But if I ask you about this molecule, is this molecule polar? You would say no. Okay? Because it's being pulled in equal and opposite directions, which means there's no net polarity there. Okay? Not a huge deal. We don't cover that too hard on the test, but it's something to consider. Gonna go back to presenting. Actually, no, I'll go ahead and present. Just know that I'm probably gonna have to come back pretty soon. Okay, so molecules are going to form 3D shapes. When you have more than 2 atoms in a molecule, you have to consider the 3D arrangement of that molecule. It's called the bond geometry. Okay, and you can find those 3D shapes by doing the Lewis structures. And if you know the number of bonding areas and the number of lone pairs of electrons on the central atom, you know the 3D shape. So notice I said bonding areas and not number of bonds, because a double bond is the exact same as a single bond. Okay, I want to repeat that. A double bond behaves the exact same way in terms of bond geometry as a single bond does. Okay. And as we said earlier, bond geometry is important to polarity. Okay. So CO2 has two double bonded polar bonds that pull in equal and opposite directions. And if you're dealing with a symmetrical molecule, it's going to be nonpolar. That's the easiest way to think about it. Okay. NH3 has 3 single bonded hydrogens. This is how NH3 would actually look. Now, what this little wedge means here, that means that it's coming towards you. And then this little dashed line means it's going away from you. So I'm not sure about you guys, but if you guys have ever seen one of those little spider massagers, I'm not sure. Very few people have, but they have like a central bond and then like 3 little legs and 3 little spears on the end. It kind of looks like that. Kind of looks like a pyramid without a top to it. Okay. If I ask you if this was polar or nonpolar, what you would say is polar, because each N and H bond is polar. Now they pull each other equally to the sides, but they end up having a net direction up because all of them are pulling up. Okay. And not to mention the unshared pair of electrons pull really, really, really hard. Okay. Just already talked about all that. Frequently, you'll have double bonds, 4 electrons, and you'll have 2 from each atoms. Do know that sometimes, especially in the case of ions, you might end up not, quote unquote, having an equal sharing of electrons. And we'll see that a little bit later when we talk about resonance structures. Okay. Those 4 electrons will be shared equally among the bottom bonded atoms. When I say equally, that not, I'm gonna actually exit that out. It's because not technically equally sometimes. You're gonna follow the same rules for triple bonds. Molecules are generally symmetrical. That's a great hint for drawing structures. So you see how this is not a symmetrical structure? Like, in other words, it's not anagrammed. Like, it doesn't go the same backwards as forwards. It's usually OCO and not COO. Now, when I say symmetrical, that has bearing to the polarity. What I mean is more about, just the order of the elements. Okay. Do these examples on your own. I've already done a few examples. I'll do H2O in a second, but I'm going to talk about resonance structures first. So, resonance structures. That means the same molecule can have more than one acceptable configuration. Okay. So, if you would like to see the electron configuration for carbonate, this is carbonate. Now, you'll notice it has a charge little symbol up there. That's telling me I'm getting 2 electrons from somewhere. That generally means it's bonded to something else. So do know that those electrons aren't just coming from nowhere. What generally will happen is, instead of this carbonate atom being bonded with a double bond like this, never mind, I'm not going to go down that. That's too advanced. Okay. The same molecule can have more than one acceptable configuration. So what that means is that this O does not like the fact that it's sharing more of its electrons with C than all the other O's are. So it's like, that's not fair. Just like when you guys complain about a teacher telling you to not talk, you say, well, everybody else is talking. It's like, well, everybody else doesn't have to share this many. So what they do is they share that burden, and it keeps going back and forth as they're sharing very, very quickly. That's why it's called resonance. they're resonating between these three states, okay? And now, how do I know how many resonance structures are here? Well, the question is, how many places can that double bond go? 1, 2, 3. Each of these is a resonance structure, okay? And the total resonance structure is all of them together. And this is exactly how you'd write it. You would draw one structure, then you would draw little arrows, draw another structure, little arrows, and draw another structure. If it had a charge, you'd put a charge to the top right, okay? And if I had a cation, notice this is an anion. If I had a cation, I would be taking electrons away from the structure. I wouldn't be throwing 2 extra in, okay? And if you try to do this on your own, which I'm going to do and show you how to do this a little bit later, you would notice that I don't have enough electrons to make this work without the ions, okay? What this means is it from anywhere means I can put them anywhere into my structure that I want from the ion, okay? And now this is where all this applies. The reason we use Lewis structures is to get to VSEPR. Now, on specifically talking about VSEPR, which is bond geometry, we do not harp on that on the test too much because there's just so much stuff you have to remember. I don't just want you to kill yourself trying to remember that stuff when you could be actually learning the material. Okay, because I know I know that you guys are probably going to throw that out of your mind the moment you leave the class. Okay, now if you're interested in exactly how many questions are over each subject, look at the Canvas test review document in the modules tab, and then that'll help you out. Okay. So valence shell electron pair repulsion. Okay, bonding electrons and lone pairs repel each other, and you attempt to get the structure where they can separate the most from each other. Now, we think of it as mostly 2D for our purposes, like we write it on paper. If you look to the right here, this is what that CH4 molecule I did earlier should look like. On our paper, it would kind of look like a cross. But like this, it looks like a pyramid, okay? You have the base of the pyramid down here, and then they go up to the top here, okay? And then the central atom is inside the pyramid, okay? That's called a tetrahedral bond structure. Now, why do you think it's called tetrahedral? Because tetra means 4, hedral means side. It's got 4 sides. It'll be one face here, one face there, one face on the back, and one face on the bottom, okay? That's what's called a tetrahedron or tetrahedral structure. Now, you're going to see all this junk. I'm going to actually put this as view. And I'm going to put present, okay? You see this? You will need to copy down to here, okay? It ends at angular. Do know that angular and bent are quite frequently synonymous, okay? Oop. Accident. That's an accident. Backspace. And if I look at the structures, you can tell why. Angular and bent, okay? Now, the bond angles will be slightly different. If I will not try to trick you up on a test, I think if I asked you this on a test or a quiz, the answer for example, H2O will be water, okay? Now, how do I read this big document here? First off, how many bonding areas do I have, okay? It's not going to be bonding electron pairs. I don't like that. It will be bonding areas. Why is bonding electron pairs wrong? Because remember how we talked about CO2? CO2 actually has 4 bonding electron pairs. You notice how that would be wrong? But it only has 2 bonding areas, okay? That tells us what the structure of it's going to be. It's going to be linear. It had no lone pairs, and it had 2 bonding areas, so it's linear. You don't really need to know what the steric number is. Bond angles. You will need to know these, okay? So just kind of get acquainted with them. You need to know these first 6, okay? Next, what if I was talking about that NH3 we did earlier, or NF3, I think it was. I had 3 bonding areas. I had 1 lone pair. Okay? So that tells you I'm dealing with a trigonal pyramidal. And look, it kind of looks like a tetrahedral molecule. But you'll see this little color right here is yellow. The reason it's yellow is because it's a lone pair. It pushes a little bit extra. And notice that the bond angle is a little bit different here. Okay? And if you're wondering what the bond angle is, it's the space between each of these bonds. Okay? It's 177 degrees between each of those bonds. Okay? So you would just look and do the Lewis structure, and you would see how many lone pairs that Lewis structure have, how many bonding electron pairs does that Lewis structure have, and then it tells you what your shape is, gives you an example of the shape, and it also does the bond angle for you. So this is a very helpful tool that you can use. Okay. And then that's all we have. So if you have any questions, let me know. Now I am going to stop presenting, and I am going to do a resonance structure of CO3, and then we will be done for this unit. Yeah, we'll be done for this unit. It will be the end of Unit 2. If I had to guess, the end of Unit 2 should come place somewhere like in the October 21st to 28 area. It just depends on how you guys are doing, okay? So first off, CO3 2-. I know that C is going to have 4 dots. Now notice I put my dots where I know they're going to end up being because I know where they're going to go. Sometimes I don't, just to keep you guys on your toes, to like oh, I messed that up right there. Okay, so O has 6 valence electrons because it's in group 16. So I'm gonna go ahead and put those 2 there. This O has 6, and this well, that's dots from left over from another place. So and this O has 6. Now you're gonna notice that there's a problem here. Oh, you can't really see. There's a problem here, okay? There. By the way, I'll make everything a little bit darker so you can see. That's a little bit better. You can see all of them now. Okay, so you're going to notice that O and this O is short of an electron, okay? If you count them up, I only have 7 here. I only have 7 there. And I shouldn't have any odd numbers of electrons. That's a dead giveaway that something's wrong. If I have odd numbers, that tells me that something's wrong because electrons always have to appear in pairs. They should be even numbers, not odd numbers, okay? So where do I get these electrons from? Well, you have to remember that this is carbonate. So if I'm dealing with carbonate, I actually have a 2- charge on it up there, okay? That means I got 2 extra electrons from somewhere. Remember, when I gain that negativity, that means I gain electrons, okay? So I just throw them in here where I need electrons, okay? And that helps me make bonds. Now, how did I know to throw it in like that? Well, because I knew I couldn't get octets on those. Now, you can go through and play with it and see if you can try to get octets on those. But you're going to notice that with odd numbers of electrons, no way can you get everything happy. Okay, and I can't just I can't have O give away an electron to C. That makes O very unhappy to just give an electron away for no reason. Okay, and C just can't give an electron away to O either. Like a lot of people, what they try to do is they just try to take an extra electron off of C. But when you take that extra electron off of C, you make it so I can't bond to the other O's too. So no matter what way you go, you're going to end up messing yourself up if you don't use the ions right. Okay, so that's what it looks like. Now let's count to make sure we have 8. 6 in lone pair, 2 in bonding. 4 in lone pair, 4 in bonding. 6 in lone pairs, 2 in bonding. So all of those have 8. Well, let's make sure that C has 8. Okay, 1, 2, 3, 4, 5, 6, 7, 8. That means everything's got an octet. Everything's happy. Let me know if you have questions. I sent out a school email, and I think I've got 70 emails right now. So I'm going to go ahead and get on that. In the last 50 minutes, I've gotten 70 emails. So I do know that you can send me questions for whatever you want. If you guys want to talk about any games that are up, I'm sure we're by the time you're watching this, we're in the middle of football season, so I'll be all about the Titans. Just let me know if you need any help. Send me an email. Talk to you guys later. Have a great day.